Hello and welcome. Today we're going to be talking about using matrices and this idea of row operations to solve linear systems. So this whole topic is really called, it's the method of Gaussian elimination. All right, so we have a couple things here. One, we're talking about linear systems, and if you've seen my previous video on introductions, you know what a linear system is, okay? And then we're going to talk about a couple other objects here. We're going to talk about matrices, and that's going to be more of a convenience tool right now. And row operations is a set of mathematical operations that we're going to do on our matrices. And the whole procedure will be called Gaussian elimination. So let's talk about linear systems. So LS, that's going to be my linear system. And I'm going to write down a specific example here. We're going to talk about, let's talk about this. We're going to talk about x plus 3y is equal to 9. And this is going to, and then we're having another line here, another linear equation in our linear system. It's going to be 2x plus y is equal to 8. All right, so this is a system. This is actually, there'll be two equations and then two unknowns. And the question we always have is, what is S, the solution space? I'm going to call it solution set. Okay. And this S is going to be, if I'm going to call this system LS, it's going to be a set of pairs x comma y. That's the type of thing that we're looking for, is a combination of x's and y's, such that the LS of x and y is satisfied. Okay, so that's what we're looking for. All right, so now we're going to talk about the way we've written this. You see, if things are highly constrained, we see right here that there's this is the x column, and there's y's here in a column. I can put a little dotted line around that, right? And then there's a column there. You can think of this as a column. And then over here we have, on the other side of the equal sign, really this is what we just call the right-hand side. All right, and because we have everything in a nice organized position, we can actually use this idea of what's called a matrix. And that's just an array of numbers in a grid. And what we can say is then it has rows, and that's of course going to be our linear equations. In this case, in this particular example, we have 2 rows. And then finally we also have columns. And those columns represent the variables it represents the different variables. So in this case we have x and y. All right, and so we have to give them a position. So we'll call 1, that's going to be x, and the column 2, that'll be everything involving y. And we see here the x's are actually, and the y's here are actually redundant. We really are just looking at the coefficients. So in this case there's a 2, there's a 1, there's a 3. So we can write it as this, a matrix, call it this. I can write our linear system now can be written as just 1, and that's just 1x there. And then in the second column of the first row, we'll put a 3 for 3y, and then we'll put a 9 over here. Sometimes people put a little dotted line there to help organize our work. So we know that this is going to be the x column, that's y, and that's right-hand side. Okay, and we go down to the second row. We see that there's a 2, and then there's a 1 for the y here, and then finally an 8. And then we'll put another bracket on that side, and that organizes our information. And this, of course, contains all the same information as the linear system, provided we have the convention that this first row is all x variable stuff, and the first column here is all x variable, and y is always there. All right, as long as we've organized things, we keep our columns consistent, then it contains all the same information. And it's clearly a more efficient format to write the thing. I don't need to write x every time and y every time I do these operations. So let's go to another page and now talk about what to do. Okay, so I'm going to rewrite my linear system. I'm going to put x plus 3y is equal to 9. And then I'm going to put 2x plus y is equal to 8. And then, of course, what we've done is change this to a matrix notation. We have a 1, 2, 3, 1, 9, 8. That's just a more efficient notation. Now, of course, back to our question, okay, so what I want to know is, what's the solution? What x, y's solve this equation? So now many of you at this point have probably solved this by doing some sort of substitution method. But we want to do something more formal. We want to actually come up with so what we want is a formal procedure to find S that works for all linear systems. Okay, even very large ones. Very large LS's. Okay, so right now, of course, this is not a large linear system, but I think this is good and instructive to work with a small one at first. And then we can expand out to a large linear system a little later. Okay, so a formal procedure. So let's go back to basic algebra. So back when you were in high school or grade school or whenever you were learning algebra, of course, the golden rule is, of course, if you have an equation, what you do is always do the same thing to both sides. Okay, both sides of the equation. Okay, and that was sort of, if you want to think of it, this is really what we call the golden rule. That's the golden rule of linear algebra, or the golden rule of algebra, right? And so, first of all, we know, of course, obviously, this helps us find answers to equations. So, of course, if I have x plus 3 is equal to 5, we can use this golden rule. Again, this is a very simple case. What I can do is, of course, add, or I could subtract 3 from both sides. So I add minus 3 to both sides of the equation. Then I get x is equal to 5 minus 3, which is 2. Now see, the key was we added a minus 3 to both sides of the equation. And what this did was, it preserved the solution. So x equals 2 was the solution. It was always there. And by adding a negative 3 to both sides, I didn't change the solution. And this is, of course, why the golden rule is so important. And I'm going to write this down, is that it actually preserves the solution. Okay? So, provided I do the same thing to both sides of an equation, it preserves the solution. And we write it in our other notation, basically S, our set of solutions here, won't change. And that's, of course, what we want. Now, this equation, we don't know what the answer to this equation. Provided we always do the same things to both sides of these equations, we're not going to change S. And whatever we do to solve this equation, we want that to be our golden rule. Okay, so now let's talk about how to do this. What are those operations? So we saw here already, adding numbers to both sides. As long as we added the same number to both sides, didn't change anything. Okay. We can do some other things now. We could also, of course, multiply both sides of the equation by the same number. That would also, it wouldn't change the solution. And of course, we can do a myriad of other things. We could divide. We could do all sorts of stuff. So let's now go to another page and talk about this in a little bit more formally. Okay, so what are the rules? So what are the rules for our operations? In fact, we're going to call them the row operations. Okay, so these row operations are essentially just fancy. It's a more buttoned up way of describing this idea of always doing the same things to both sides of the equation. So the row operations are as follows. The first row operation is we can always scalar multiply. So we can always so for any row, any line of our equation, we can always we can multiply a scalar, and that should be a non-zero scalar. Non-zero by any row. Okay, and the second thing we can always do is exchange rows. Okay, and we know that, and finally 3, what we can do is actually add scalar multiple rows, or sorry. We can add scalar multiples of rows to each other. All right, so let's elaborate on what this means. What we're really doing is here, for this, multiplying a scalar, what we're doing is we're, say, taking a row 1 and multiplying it by a constant. We'll call it A. And that's going to become my new row 1. All right? Here, what I'm doing is really a swap. So I'm saying take row 1 is now going to be row 2, and row 2 is going to be row 1. I'm using arrows to represent that transformation from one to the other. And here, adding scalar multiples of rows to each other. All right, let's talk about that. This is obviously the one that I think maybe has the most going on in it. What we can do is, of course, take A, some scalar multiple that's non-zero, times a row 1, for instance, and then add it to row 2, and that will become my new row 2. All right, and so with all of these, it preserves S, the solution space, or the solution set. So let's look at an example really quick. Again, we'll write down our matrix, this example we had, 1, 2, 3, 1. I'll put my little dotted line. Some people put that dotted line there. Sometimes they just leave it alone. I'm going to put the dotted line there just to be a little bit more clear about that this is the left-hand side of the equation, that's the right hand. Okay, so let's talk about multiplying a row. Okay, so I can, for instance, I can now, I want to change this a bit. I want to take row 1, I'm going to multiply it by, oh, let's say, I'll multiply it by 5. Okay, and I want that to be my new row 1. All right, so what I would do then is write 5 times 15. Sorry, 5 times 1 is 5, and then 3 times 5 is 15, and then 9 times 5, that's going to be 45. When I write this back out again, of course, we know this is going to be 5x plus 15y equals 45. Nothing about this equation up there is different. It has the same information in it, and of course it has the same solutions as the original one. Okay, fine. And so that's the scalar, and of course we can exchange rows. That won't change the information of this problem, but I'll leave that alone for now. Now I want to talk about scalar multiples. I'll do another one. So let's say now I want to do another operation, another row operation. that preserves the solution set to the system. Okay, so let's say I want to take maybe 3 times row 1 and then add that to row 2, and that's going to be my new row 2. All right, let's do that. All right, and I always like to, on next to my matrix, when I'll put like an arrow or something connecting these. What I'm really saying is that they both have the same solution by putting that arrow. In fact, later on we'll change that to another notation, but we'll just use your arrows for now. But for what we're going to do now is we're going to do this operation. I always like to actually write the operation next to the matrix, so I know how to get between these two matrices. So of course I'm going to add three times row 1 to row 2, and that's going to be my new row 2. All right, 3 times 1 is 3, plus 2 is how many? That's going to be 5, right? Row 1 is going to stay the same, though. I can just write that up there right now. All right, and then, of course, 3 times 3, that's a 9, plus 1, that's going to be 10, right there. And finally, 3 times 9, that's going to be 27, plus 8, that's going to be 35. Okay, and I can put that little dotted line there. Oh, I got to put my dotted line there. All right, and so again, all these matrices here have the same solution. They are different linear systems, yet they share the same solution space. All right, so those are row operations. Now, how do we use them? So row operations are a tool. And it begs the question then, how to use them to find S. And clearly what we have to do is use row ops. We have to use row operations to simplify the linear system, okay, and therefore expose the solution space. Okay, so how do we do that? And the goal then, and this is called Gaussian elimination. And I'll summarize what Gaussian elimination is. Effectively what it is that we want to use row operations to make zeros in the lower left corner of the matrix. Okay, and then so that's going to be the first goal. I'm going to call that goal 1. Okay, and I'll talk about goal 2 in a second. But that's the first thing we need to do with this operation. So let's go back to our linear system. Again, we had our linear system was. Let's go to our example. We had 1, 3, 2, 1. And then we'll put our dotted line, and then a 9, and then an 8. Okay, so our row operations. I want to find a row operation that will put a 0 in the lower left corner of our system. Okay, so what I want to do is I want to make that 0. Make 0. That's my goal. All right, so I can see if I multiply row 1 by -2 and then add it to row 2, that's going to make that 0. So I'll write that down here. So I'm going to say row 1 times -2 plus row 1. So I'm going to put an arrow there plus row 2, and that's going to be my new row 2. And what that's going to do is put a 0 in that lower corner. So of course row 1 is going to stay the same. And then what we're going to do is we're going to put that 0 there by design. And then we have to figure out what the rest of them are. So of course I'm multiplying -2 by 3, and then adding it to 1, and so that's going to give me, so that'll be a negative 6 plus 1, that'll become a negative 5. And then we see here, this is going to be a negative 2, so that'll be negative 18 plus 8, that will be negative 10. All right, that looks pretty good. We have that 0 there. So the idea is that this does, in fact, simplify the linear system. They both have the same solutions, but this one is getting a little bit simpler because now this equation is very simple. The next thing I might want to do then is, and now I'm going to go put an arrow there, is that I see that there's a negative 5 and a negative 10 there. I see that there's a common factor of negative 5, so I'm going to use one of my other row operations, that of scalar multiplication now, to simplify that. So what I'm going to do is actually going to multiply by negative 1/5 times row 2, and that's going to be my new row 2. And then I have 1, 0, 1, then I have a 3, 9. I haven't done anything to row 1 in a while, and this is going to be 2. All right, so now this linear system has the same solutions, but we can clearly see now that I can unwrap this now, that that's actually y is equal to 2. That's what this bottom line here is saying. So of course that is simpler. It does expose the solution that y is equal to 2. And then I can actually go back and find out what x is. So I want to take this to the next page though, and we're going to see if we can make this even simpler. So let's now go here now. What we had was, and I'm going to write out the original linear system, 1, 3, 2, 1, and then we had a 9 and an 8 on the right hand side. And we used a bunch of row operations, and we got it all the way to the point of 1, 3, 0, 1, 2, and then a 9. Okay, and of course we saw right here immediately that this meant y is equal to 2. But then the question then is, what is x equal to? Well, we can find that, but now we're going to do, so Gaussian elimination. What we'll call phase 2 is to now go up. So we put that, phase 1 was to get that 0 in that lower point, but now we want to go back up and put a 0 up in the 3 spot, and that should expose what x is. So of course what we have to do then is have to multiply negative 3 by row 2, add it to, so that's row 2 there, add it to row 1, and that will zero out that position there, and that is a 0 out, so sorry, phase 2 is to zero out any number above ones. Right, so we have to come up with some notation. We see we have these ones on the diagonal, and these are actually called leading positions. So what we call these is we call this an echelon matrix. So an echelon matrix is any matrix that has this form where there's zeros below. I could have more than that. And there's some other numbers here. So, A, B, and C. That's an echelon matrix, okay? And the reason they call it echelon is sort of like geese flying in a flock. They always fly in kind of a V pattern or a triangular pattern and a diagonal pattern like that, right? So what we want to do is now, the elimination phase 2 is to zero any number above the 1. So we always have these leading ones there. What I want to do is now I got to go up now and do Gaussian elimination to get those all 0. In this case, it's that one we want to make 0. So I'm going to add a negative 3 row 2 to row 1 and make that the new row 1. So what I can do is then go 1, 0, 1. and then that makes a 0 there. And then I multiply negative 3 by 2, and that gives me negative 6. And I add it to 9, that gives me a positive 3. And now we see here that y is in fact 2, and that x is equal to 3. All right, there's our solution. So just to put it in form, s is equal to 3 comma 2, where that's x and this is y. So that's my solution set. And this is a case where we have one unique solution. Okay, and that's how we can do this. Now, in later videos, I'll do Gaussian elimination. And what we'll do is we'll do it on a larger system where things are a little bit more complicated. There are more steps, but the procedure is the same. So again, in the last little bit here, I'm going to talk about one thing. So so I'm going to talk about the idea of an echelon matrix. So there's this. So once we get zeros, so when you do Gauss phase 1, which is zeros in lower triangle, and then you do phase 2, and that is all leading entries in H echelon. What you do is you make zeros above. Okay, and that's of course going back up to make those zeros. All right, once you do that, they say, oh, what we call it, we say that the matrix is in reduced row echelon form. And in later videos, I'm going to give a more elaborate understanding of this. We'll see more examples where what this form is, and sometimes we'll call it by the simple number RR, or the simple acronym RREF, reduced row echelon form. So we'll talk about that in later videos more. But that is the procedure to put a matrix in reduced row echelon form is using this Gaussian elimination. And elimination means, of course, use row operations to create zeros in the matrix. And that, of course, simplifies the matrix so you can expose the solution. Thank you very much.